Well, thank you very much, Mr. Chairman. This is some of the work also we did on storage of batteries, where there are some pollutants coming out of these batteries, and my students was the first author, and my colleague and myself had this work done. In many of the battery storage areas, there are some explosions because of the gases and because of the inadequate ventilation of the storage rooms. Here are some of the battery storage in single row and also in a double stacking. We have, of course, guidelines. Actually, have a guideline for space recommended for the concentration of the gases produced. Now we have different methodologies and different ventilation systems, like displacement ventilation and mixing ventilation. Also, we have an overhead flow or underfloor flow. We have local ventilation, and we have local ventilation using air curtains. So we did some literature review on the research carried out, whether experimental or numerical. These are the governing equations that you heard me talking about earlier today, and it's the continuity and the three momentum equations in the three directions, taking into account the gravity, pressure, and various stresses. So this is the energy transport equation, and also the species transport equation. And we solve these into a network or a grid of points using commercial software. So here we have the ventilation model room, where we have an inlet and outlet, and we try to predict the air distribution inside. So the circles here, the squares, are the experiments done by Gasper, while the solid lines are different predictions using various versions of turbulence models, like these are the realizable and RNG turbulence model. A turbulence model is a model that assumes the flow behaves in a certain way and calculates the viscosity or the shear stress based on two parameters, in this case, which is the kinetic energy of turbulence K and its dissipation rate, which is epsilon. So it is a very famous two-equation turbulence model that has been proposed by Imperial College back in 1972. It's still alive till now. There are more modifications of this model. Then we have the standard K-epsilon model, and then we have the RNG and realizable. Of course, we have other models of turbulence like large eddy simulation, real stress, and normalized stress, and others. So here we see that the errors can be of the order of 0.944%. Now let us go directly to the case where we are simulating. So in this case, we have racks of batteries, typical batteries like your car battery, and these are typically used when you are having UPS and power supply in a place where you don't want the electricity to be cut, usually in IT rooms and things like that. So here we have a five-room battery set, and this is the surface, and then we have symmetry axis. So we have 100 batteries, 20 batteries per rack. We assume various velocities at the inlet, size of the grid. This is our design parameters listed in here. Of course, you can use, when we're using numerical method, what we do actually is we are solving a differential equation at various grid nodes. If I use infinitely large grid nodes, I am going to very near to the correct solution. If I'm taking very small number of nodes, I'm not representing reality. Of course, when you are doing a calculation on a computer or a laptop, you would love to use a smaller number of grids, so the equations will be solved quicker, with no problems of divergence. Residuals will tend to converge easier because you are solving at less number of nodes. But to get results that are not dependent on the number of grids, you have to do this exercise. We call this exercise grid independence test. For example, in this case, we use 1.35 million grid nodes, 2.2, 2.5, 4. You can go up to 10 million, 20 million, whatever. But we have to stop at certain time when the results do not change. And to us, as people working with numerical, we can say that the grid, the solution is grid independent. Of course, my students usually try to cheat by saying, okay, it's good, sir. I said, how good? Mind you, when you are doing numerical computations, we know for sure there are discrepancies. But it will be very good if the predictions or the computation are giving us qualitatively the same trend. The velocity is going this way experimentally, and also it's going this way computation, and it can be analyzed with the logic that we learn from the intuitive ideas of our basic engineering. So here, for example, the objective is to study the effect of changing the air. ACH is air change per hour. If I'm ventilating this room, then I would like to change the air in this room 2 times, 3 times, 5 times per hour. Actually, give us a value for each application. Of course, if you put higher air change per hour, you are going to use a bigger fan, you're going to pay more money and more energy. So we'd like to reduce this. On the other hand, the indoor air quality people would love very much to put a lot of air inside, so you are going to dilute any pollution that will exist from the batteries. So it's a compromise between indoor air quality and energy as it used to be, and that's where it actually comes in. So here, for example, these are the cases that we investigated. Different design of the air supply into the room, and number, location. We take into account, of course, the location of the outlets, lights, inlets of air to the room. Here we go. These are some of the concentration of the hydrogen, and we get the concentration of the hydrogen from the production, from the batteries. We know this value for each battery, and we see how it migrates into the room. And of course, codes give us some values of the concentration that should not be exceeded in order for life saving. So here, for example, these are the H2 concentration at various locations, which has an average of 1.77%. Velocity magnitude, you can see here, for example, the air coming from the outlet, and it goes this way. So these are the velocity magnitudes. Now here we have the actually standard guideline value, threshold level, and here we have, if we have 4 air change, we are exceeding, but if we have 6 air change, we are just about right. 8 air changes will be less than the threshold level. So it is recommended to use 8, but for energy saving, we use 6 air changes. You know, when I go to design a project for any client, I specify the value of air change rate at 6, for example. The client will feel that the fans we are putting is large. So I said, why? This is more money, it's more energy. So you have to discuss and try to explain why we are using this air change rates. Here, for example, this is another typical case where we have the batteries arranged in a certain way, and you have the lights and you have the inlet. So here we get also the concentration of the H2 cross sections, and you can see the way the jet comes out of the wall. Glossy magnitudes, and as these are the batteries, and this is the air distribution. Here another case. So it's like a parametric investigation to see which one will give you the better indoor air quality. Here, for example, this is the threshold level of ASHRAE, ASHRAE 21, which is the standard. It's a guideline for the battery storage at a certain location. So, and on, we try to show how we can use computational techniques to give us a better idea about what's happening in battery storage, if it is a single rack or double rack. Here, if you have the air coming from the ceiling or if it is coming from the sides. I'm not going to bore you with more of these, but just trying to show you the capabilities that are possible to do with computational techniques. What matters is how we can predict the various variation. You can see the variation of the concentration along the space in the room. Lost magnitudes again for different cases. And also comparison relative to the threshold of ASHRAE Guide 2020. Now if we have double stack, which means we have double rack of batteries, and we use this for compactness, what will happen here? We have case 11 and case 9, and this is the average concentration of H2O. Here the details. It's basically a fluid dynamics case with the concentration. So you're solving your continuity equation, momentum equation, and also the concentration of the species. So it's all the same but different application, different air change rates. So if you look into any of the ASHRAE guides, you will find that for each particular case, you have the recommended air change per hour, and it is being tested for various cases. So to be short, the ventilation rate is increasingly proportional to the hydrogen concentration, and it's a nonlinear relation between these two parameters. Locating the inlet grill at the lower wall section and outlet grill of the upper is a good will offer a good ventilation and will reduce the hydrogen concentration percentage. With that, also like to split the long single row into two halves of the vertical stacking. Will make the room smaller in size, but will make also utilization of the height. That's what some recommendation for future work is to study the possibility of better ventilation procedures in these rooms. I'd like to thank you and for your patience. The reason for the reason for the advancement of computational techniques these days is the strong improvement in computational capabilities. I told you earlier today when I did some calculations in '73, I used the 8,000 grid nodes. When I did because I did the air conditioning for the stadium in Qatar where they're going to play the football in 2020, it's my design. So I used 20 million grid nodes to simulate stadium, open roof, no roof, and still it's air conditioned. And that's the real case. I used the same technique to model the St. Mary's Orthodox Church in Cairo. This is the church built on the spot where Christ as a baby and Mary came to Egypt. So they spent a few nights in a certain area in Cairo by the Nile, and they built a church. The church is 1,500 years old. I was honored and blessed that the Pope approved me to design the air conditioning for this archaeological church, which I did. And it's working now for 2 years, thanks God. But you can imagine how you feel the strength of a tool I used to design, to do optimization. We had a robotic where we used inside the church to measure, so we validated our computation. That was done in about 5 years ago. I used the same technique also to design the air conditioning for the Grand Mosque in Mecca. The Grand Mosque in Mecca, where Muslims go there, used to house 500,000 prayers. The expansion is to house 1.5 million. So they are expanding it. And the design, I did the revision of the design. I had to calculate the energy efficiency for this design to be green. That's a question asked by the King of Saudi Arabia for me. Is it green? So sometimes we tell our students, the undergraduate and graduate, go and do energy efficiency. Make it green. But sometimes you are subjected to a project, a real life project. Exactly like when I did the ventilation of the tombs of the Valley of the Kings in Egypt. King Ramses, King Tutankhamun, where are 5,000 years old tombs, and you have walls made of limestone, and when visitors go there, they prescribe. So water vapor comes out of the mouth, and it condenses on the wall. So all the paintings that were 5,000 years old go away, deteriorate. So they called us. Of course, nobody believes in university professors. So I went there and we tried to get a solution, and I have 16 tombs to work on. I finished one, which is Hor Moheb. It's called KV57, and it's working. They used to have to put their hands on the wall like this, and comes water. So the solution was to limit the number of visitors, to do a ventilation system in order to, so that you have the fans operating, then the relative humidity goes down, then you allow visitors to go, and so on. And you do this cycle. So that tells you how computational techniques, of course experiments will be number one, but also computational techniques can be very helpful. Thank you very much.